Deep networks are nonlinear, yet locally linear. This paradox enables efficient adversarial attacks. We'll dissect the math, show how it breaks quant models, and test defenses. Consider a deep network as a function mapping input space to output probabilities. Despite its global nonlinearity, within a tiny neighborhood around any point, it behaves almost linearly. This is because activation functions like ReLU are piecewise linear, and the network is a composition of such pieces. The consequence is that the gradient, which points in the direction of steepest loss increase, is a reliable guide for crafting perturbations. An attacker can push the input along this gradient to flip the prediction with minimal change. The key tool is the first-order Taylor expansion. For a classifier f, loss L, input x, and true label y, we approximate the loss at a perturbed input x plus delta. The expansion shows that the change in loss is approximately the gradient of the loss with respect to the input, dotted with the perturbation. This linear approximation is accurate for small delta, which is exactly the regime of adversarial examples. To maximize the loss increase, we choose the perturbation delta as epsilon times the sign of the gradient. This is the fast gradient sign method, or FGSM. The resulting loss increase is epsilon times the L1 norm of the gradient. For a linear model, this is exact. For ReLU networks, it works because of local linearity. The epsilon controls the perturbation size, often set to a small value like 0.01, which is imperceptible to humans but enough to fool the model. The increase in loss is proportional to epsilon and the L1 norm of the gradient. This shows that if the gradient norm is large, even a tiny epsilon can cause a significant loss increase, flipping the classification. This is why adversarial examples are so effective. They exploit the direction of steepest ascent, not random noise. ReLU networks are piecewise linear, meaning the decision boundary is a collection of hyperplanes. Within a linear region, the model is exactly linear, so the gradient is constant. This makes the FGSM attack exact within that region. Even outside, the approximation holds for small perturbations. The vulnerability is inherent to the architecture, not a bug in training. Imagine an LSTM model predicting stock price direction. An attacker can craft adversarial examples by submitting a few orders that slightly alter the order book features. Since epsilon can be as small as 1/10 of the tick size, the manipulation is imperceptible. The model flips from up to down, causing the victim's algorithm to trade incorrectly. This is a realistic threat to quantitative trading systems. The counterintuitive conclusion is that deep learning quant models are inherently fragile to adversarial attacks. This is not a matter of adding more data or better hyperparameters, it's a geometric property. The model's decision boundary is so close to the data manifold that a tiny push in the wrong direction crosses it. This fragility is a fundamental challenge for deploying AI in finance. The simplest defense is adversarial training. Augment the training set with adversarial examples. This makes the model more robust to such perturbations, but it comes at a cost. The model's accuracy on clean data often drops, because it learns to be less sensitive to small changes, which can also reduce its discriminative power. It's a trade-off between robustness and accuracy. More practical defenses include ensemble models, which average predictions from multiple networks, and robust optimization, such as Wasserstein robust optimization. Ensembles reduce the chance that all models are fooled by the same perturbation. Wasserstein robust optimization explicitly trains the model to be robust to perturbations within a certain distance, but it is computationally expensive. These methods offer stronger robustness at a higher cost. Let's compare the two main defense strategies. Adversarial training is simple and fast, but it only defends against the specific attack used in training. Ensemble methods are more general but require multiple models. Wasserstein robust optimization provides a theoretical guarantee but is extremely slow. The choice depends on the threat model and computational budget. In summary, adversarial examples are not a curiosity but a geometric inevitability. Deep networks' local linearity makes them vulnerable to gradient-based attacks, which are cheap and effective. For financial quant models, this is a real risk that can be exploited with minimal market impact. Defenses exist, but they come with trade-offs. As AI becomes more embedded in finance, understanding and mitigating these vulnerabilities is not optional, it's essential. We'll continue to explore the intersection of AI and markets. Markets reward discipline, not certainty. If this analysis helped, like the video and subscribe to DeepQuant. Tell us in the comments which market idea we should test next. Evidence beats noise. Control risk before chasing returns.